Today we will look at the impulse momentum theorem. Previously we saw how to set up the impulse and momentum, change in momentum. We found in the previous video lesson how we find the impulse and how we find the change in momentum. Now we'll put it together. Again, the impulse momentum theorem states that if I have an object here that has a certain momentum, let's say of 5 kgms, it's moving, and I apply a force on it of, let's say, 10 newtons for 5 seconds. That means I did an impulse of 50 newton seconds on this. And so because I applied an impulse of 50 newton seconds, the momentum will increase by 50 and will now be 55 kgms. Now it might bother you to say, hey, wait a second, how are you equating Newton seconds to kgms when we have an equation like this? Not only should the values of both sides be equal, but even the units. So how is this working out? Well, it turns out that Newton seconds is the same as kgms. Newtons, if you remember, is kilograms meters per second squared. If you ever forget that, just remember F equals ma, m is kilograms, and a is meters per second squared. And so if I take kilograms meters per second squared, which is newtons, and I multiply it by seconds, 1 second cancels from there, leaving me with kgms. So we see that Newton seconds and kgms are the same units. Either one can be used as interchangeable, but when we talk about momentum, we like to use kgms because it's m times v. And when we talk about impulse, we like to use Newton seconds because it's force times time. Okay, now instead of writing many different equations relating all these together, I generally give my students, well, really this equation right here, which is one long equation. It's showing that the impulse is equal to force times time, which is equal to change in momentum, which is simply pf minus pi, which could be written as mvf minus vi or m delta v. I'm going to paste this in all of our question problems so I can show you how we use this to simply solve for problems. Instead of giving you 8 or 10 different equations, just give you one this way, and you could use the parts of the equation that you need. Okay, so let's start with the first one. Calculate the impulse of a 50 kg object that decreases velocity from 200 meters per second to 50 meters per second. Now obviously this object was moving in a certain direction, and we applied an impulse or a force in the opposite direction to slow it down. Well, you might think, hey, wait a minute, if I want to find impulse, I need to find force and time, but neither of them are given to me here. And no worries, we know that that's the same as the change in momentum, and that is something we can figure out here. So let's just figure out the change in momentum. The change in momentum is m vf minus vi, which is 50, times vf is 50 minus 200, which gives you 50 times negative 150, which is 7,500 kgms. Since J, which is F dot T, is equal to the change in momentum, that means that the impulse is the same as the change in momentum. So our impulse would have been negative 7,500 Newton seconds. Okay, so that is the impulse needed to convert the speed of this from 200 meters per second to 50 meters per second. How I applied this force is not known. Maybe I applied 7,500 newtons for 1 second. Maybe I applied 750 newtons for 10 seconds. But I do know that the total impulse was equal to this. Okay? Pretty straightforward. Next we say, calculate the change in momentum of a ball hitting a wall with 500 newtons of force with 0.2 seconds. Again, you might say, change in momentum, I need kg, I need meters per second. I don't have either of them. No worries. Just remember that the impulse is equal to the change in momentum, always. So if I have a force of 500 newtons for 0.2 seconds, that is 100 Newton seconds, and that would tell you that my change in momentum was equal to 100 kg/ms. Okay, again, these units are interchangeable, but when we talk about momentum, we like to use these units. When we talk about impulse, we like to use these units. Okay, let's look at some more examples. A 0.7 kg soccer ball experiences an impulse of 28 Newton seconds. Determine the momentum change. I hope you realize there's no math needed to be done here at all. If the impulse was 28 Newton seconds, then the change in momentum will also be 28 Newton seconds. So the change in momentum, my delta P would equal to 28 kg/ms. Okay? Really, really simple. No math was needed here. It usually traps the kids when they're trying to figure out, wait a second, I need to use this somewhere or multiply them or whatever. Nope, nothing else. Just pay attention that the impulse is this, momentum change will be the same. A force of 200 newtons acts on a 250 kg ball for 0.5 seconds. Calculate its change in velocity. So I look at my equation here. I say, okay, they are looking for a change in velocity. They gave me mass, time, and force. So I could use this and this. And so I set up my new equation. And that's how we use this long equation. We just use the parts that we need. I could have used them up here too. For the previous questions, just delta P is this. We could have found the change in momentum that way, and so forth. All right, so here we have a force of 200 newtons acts on a 7.2 kg ball for 0.35 seconds. Calculate its change in velocity. So since I'm just going to use those parts, I'd say F times T. I could use delta T, but if you assume that the initial time is 0, then just T is good, is equal to the M times delta V. Okay, because the reason I'm not looking for initial and final velocities because they're not asking for that. They're asking for the change in velocity, and that's sitting right there. And so my delta V would just be force times time divided by mass. All I did here was divided both of these by M. Okay, so then delta V is going to be the force, which is 200, times the time, which is 0.350, divided by the mass, which is 7.2 kg. Okay, again, our units always work out. This here is newtons. This here is seconds. Okay, and so moving on, we have 200 times 0.35 divided by 7.2, which gives me 9.72 meters per second. So this force acting on this 7.2 kg ball for 0.35 seconds will increase its velocity by 9.72 meters per second. Okay, again, it was really straightforward. All we did was we were given force, mass, time, and looking for delta V. So we have force, time, mass and delta V. And that made sense to use that part of the equation. I divided both sides by m, solve for delta V, and that's 9.72 meters per second. Okay, let's look at some more examples. A 1400 kg car is brought from 25 meters per second to 10 meters per second over a time period of 5 seconds. Determine the force experienced by the car. So again, here I have mass, VI, VF, T, and I'm looking for F. So if I look at these variables, what makes sense for me is to use this with that. Do you see? Those are brings in all the characters we need here. So force times time is equal to m VF minus VI. We are looking for F. So I could really solve for F first, divide both sides by T, and gives me force is equal to m VF minus VI over T. Now we could put in variables first and then substitute the values and then solve for the variable, but it makes more sense usually as a preferred way to solve for the variable first before we substitute the values. And so that would be 1400 times VF, which is 10 minus 25 all over T. And so that gives me 1400 times negative 15 all divided by 5. And when I put that in the calculator, 1400 times negative 15 divided by 5 gives me negative 4,200 newtons. So that is the force I need to apply for 5 seconds to slow this car down from 25 meters per second to 10 meters per second. Okay, pretty straightforward. Again, a lot of these questions can be solved using F equals ma and the kinematic equations in combination, and you could still solve for the same thing. What you could have done here is used kinematic equations to find the acceleration, multiply the acceleration by the mass to find the force. But again, we're using the impulse momentum theorem to solve the same questions, and so this is the way we want to do it. Some more examples. A 0.4 kg object moving on a frictionless surface with a speed of 30 meters per second. A force of 2 newtons is applied continually until the object comes to rest. How long was the force applied for? Again, I have mass, VI, and VF, which is 0, and we're looking for T. Here's F. Again, it makes sense since I have those variables to use this and this together. So I have force times time equals m VF minus VI. Now in this case we're looking for time, so I'm going to divide both sides by force to isolate time. Excuse me. And so T would equal to m VF minus VI over F. Plugging that in, I get 0.4 times VF is 0 minus 30 all divided by 2, which gives me 0.4 times negative 30 divided by 2, which should be 0.4 times negative 6, or we're looking for T. I I need to remember that my force is negative, so this is a negative quantity here, so that would be negative 2 newtons. If my velocity is defined as being positive in this direction, and if I'm applying a force in that direction, which is obvious because I am slowing it down, my force would be negative 2 newtons. So placing that in there, you end up with plus 6 seconds. No way, time could be negative, right? Okay, so that tells you that you would have to apply a force of 2 newtons for 6 seconds to a 0.4 kg object to slow it down from 30 meters per second to rest, to 0. Excuse me. So that completes the simple example problem. Let's look at some more. Oops, I missed one. Okay, a 0.1 kg baseball is pitched with a velocity of 35 meters per second. The batter hits it straight back with a velocity of 60 meters per second. What is the impulse on the ball? So since I'm looking for J here, and I have mass and initial velocity and final velocity, I would use these together. So J is equal to m Vf minus Vi. And that's what we're looking for, is the impulse. And so 0.1 times, and again, we've got to be careful here, Vi is 35, Vf is negative 60. Again, if the ball was going back this way at 35 meters per second and coming back this way at 60 meters per second, then this would be negative. So negative 60 minus 35, which would give me 0.1 times negative 95, which would give me negative 9.5 Newton seconds. Okay, so that would be our impulse. Now you can see that if the object was moving this way, the impulse would be in the opposite direction. And keep in mind, impulse is also a vector. J is equal to force, which is a vector, times time, which is not a vector. This is not a dot product, but a simple scalar multiplication. Okay, and so that tells us how we can find the impulse imparted onto the ball. For this question here, we have a 30 kg block moving with a velocity of 50 meters per second. And there's a force acting in the opposite direction of 8 newtons. That's slowing it down. We want to know what is the momentum after 15 seconds, after I've been applying this force for 15 seconds. So looking at the stuff I have here, I have m, Vi, and I have the force, and I have time. So I should be grabbing on to force times time equals m Vf minus Vi. And since I'm looking for final momentum, which is all of this quantity, I'm going to multiply it out. And then I'm going to add mvi to both sides. And so I get force times time plus mvi is equal to mvf. And this is exactly what I'm looking for, is my final momentum. My force is 8 newtons. It's negative 8. So negative 8 times 15 plus 30 times Vi, which is 50, is equal to mvf. Multiplying that, I get a negative 120 plus 1500, which is equal to 1380 kg ms. And that's my final momentum. Okay, so originally this block was traveling with a momentum of 30 times 50, which is 1500 kgms. After this friction force acted on it for 15 seconds, we now are left with 1380 kgms as our final momentum. Okay, hope that was straightforward enough. I have one more last one to do. A force of 60 newtons is applied for 1.5 seconds to a 49 newton object traveling at 4 meters per second. What is the final velocity of the object? Again, it makes sense since I have force and time, and this is where I'm going to get the mass from. It's a 49 newton object. So 49 newtons divided by 9.8 is going to give me 5 kg. So that's the mass I'm looking for. You have to be careful whenever they are describing an object. Sometimes they give you the mass, sometimes they give you the weight. It's very easy to see which one it is if you just look at the units. It tells you that it is the weight that was given in this case here. So again, I use Ft equals m Vf minus Vi. This is the guy I'm looking for, is my Vf. So I could rewrite that as force times time and divide both sides of these equations by m because I'm trying to isolate Vi. So I have F over T over m, Ft over m is equal to Vf minus Vi. And again, since I'm looking for Vf, I'm going to add Vi to both sides. And so I have force times time over mass plus Vi is going to give me Vf. And so if I were to look at this and fill in the values, I have 60 times 1.5 divided by 5 plus 4. And so that would give me 60 times 90 divided by 5 plus 4, which is equal to 18 plus 4, or 22 meters per second. So this object was originally traveling at 4 meters per second. I applied a force of 49 newtons. I'm sorry, a force of 60 newtons for 1.5 seconds and increased the velocity from 4 meters per second to a final velocity of 22 meters per second. Okay, so there's some examples that we just saw of how to apply the impulse momentum theorem to solve problems using this expression here. Of course, you could have them written as separate equations. I just think it's a little more easier and a little more elegant to kind of do it this way. All right, so bye for now, and I hope you learned something here.
Thank you for watching. If you liked the video or found it helpful, please like us.